my name's Christopher Collison, and we're going to continue today with the course on quantum mechanics. That is course CHMP 442 in chemistry at RIT. So the title of this lecture today is called The Rules of Quantum Mechanics, and what I want to do with you today is basically say that even though it may be difficult to understand quantum mechanics, we can nevertheless apply a series of rules of the game to certain systems. For example, the rules of chess or the rules of Monopoly. We don't really need to know how those rules were set up, but if we want to play the game, we need to know what those rules are. We need to follow those rules. So my first approach here is to state these rules of the game. We'll come back to these rules multiple times over the course of the course as we go through each chapter and as we increase the complexity of the systems that we're trying to describe. So without further ado, let me tell you the rules of quantum mechanics, and I'll put these in front of you. An extra point for the movie reference for the first two in here. I'm kind of having a bit of fun. Let me know over email what the movie reference is. But perhaps more importantly, the actual rules of quantum mechanics are described here, and we're going to go through these. You describe your systems using classical physics. You substitute the observables that we have in classical physics with a corresponding quantum mechanical operator. We'll see where those come from later in the course. From that, we're going to build the Schrödinger equation. And once we have a Schrödinger equation that's built, it's an eigenvalue problem. We're going to solve that Schrödinger equation. And we're going to apply boundary conditions to refine the solution. And that's basically it. So we're going to go through these over and over again. So remember this presentation. The movie reference might help you remember this location. We shall see. But let's go through these in a little bit more detail. So the first rule of quantum mechanics is describe your system or your systems using classical physics. So what we're going to do first is we're going to think about an electron that is set up on a butadiene molecule. Actually, that's incorrect. So the butadiene molecule would be like this. So in principle, we have an electron that could whiz backwards and forwards. This pi electron could whiz backwards and forwards over this molecule. So it'd be confined to this molecule. And so what we're going to think about first of all is, let's simplify things and think about the kinetic energy of that particular electron. So we're going to find that quantum mechanics starts with a description of the system in terms of its energy. So what does that mean? So we know that kinetic energy, by the way, is equal to half mv squared. And so if we're thinking about this electron and we're thinking about the kinetic energy, we can also, by the way, write this in terms of momentum. So because mv is equal to momentum, so the momentum is p squared. Well, p squared is m squared v squared, so we've got too many m's in there, so we need to put 2m in the denominator. So this is simply a description of our system in classical terms and the energy of that electron. So what else can we do? The next rule, we're just going to follow these rules, right? Substitute observables with the corresponding quantum mechanical operators. So what can we do here? What are the observables that we care about? Well, it turns out that the momentum here is an important observable that we can substitute for. We're going to add into here something called a quantum mechanical operator. And the quantum mechanical operator for momentum is, we're going to see how this is written as a p hat. We're going to see that that's what that operator symbol is for an operator. We put a little caret or hat on top here, and this is equal. We can look this up in a textbook. I'll explain where these come from at some point. The quantum mechanical operator for momentum is equal to minus I h bar di by dx. Okay, where does it come from? It doesn't matter. We're effectively looking up this equation. This equation is the operator for linear momentum, and what we're going to do is we're going to substitute that into our above expression. So now if we want to think about a new kinetic energy operator for this particular system, this is going to end up being, well, we've got the minus in here, so we're going to substitute this in. So we're going to square the minus, that ends up being a plus. We're going to square the I, okay, and I multiplied by itself, a square of I is equal to -1. Now we're going to square h bar, so h bar squared, and next we're going to square this particular partial derivative. Okay, so we end up with minus h bar squared di squared by dx squared. That's the p squared form, and of course we still need the 2m on the bottom in here. So this ends up being what we will call our kinetic energy operator for the system that we care about. Okay, let's come back to our next rule of quantum mechanics, and it says hence build the Schrodinger equation. So it's a very quick trip through these rules for now. So we're going to build that Schrodinger equation. What is the Schrodinger equation? So the Schrodinger equation is simply equal to H psi equals E psi. We will talk about setting this up, and we'll talk about where it comes from in the next couple of weeks. But effectively what we're going to do is we're going to say we're going to take our operator. We just developed an operator for kinetic energy. In this case, the kinetic energy operator was equal to minus h bar squared di squared by dx squared, and that was over 2m. Okay, so now what we have is an operator. Okay, we plug that in to our Schrodinger equation. So we're going to plug this in up here. We're going to apply this to some function psi, and we are told that that is equal to the energy of the system multiplied by psi. So this is the Schrodinger equation that we built using the kinetic energy operator that pertains to our electron in butadiene. So next up, what do we do now? Okay, the next up, rule number 4 in here is to solve the Schrodinger equation. It's an eigenvalue problem. So what does this mean? So if we go back to our expression in here, here's the equation that we need to solve. It's a differential equation. We need to find the solution. We need to find a solution such that when we take the second derivative of this function, we return exactly that same function over here on the right hand side. So let's come up with a possible solution. So it turns out that possible solutions include the following. So maybe e to the alpha x is a reasonable solution. When we take the first derivative, okay, take the first derivative of this function, we get alpha e to the alpha x. If we take the second derivative of this function, okay, we get alpha squared e to the alpha x. The point here is what we end up with is a constant alpha squared multiplied by a function e to the alpha x, and it turns out that this function is exactly the same as the function that we started with. So we would say this is an eigenvalue problem, this differential equation, and one of the possible solutions that we could put in here would be that psi would be equal to e to the alpha x. So that's a possible solution. So we're going to solve the Schrodinger equation. We're going to find a whole bunch of these possible solutions. Another possible solution, by the way, might be something like cosine x. Cosine, let's call it cosine alpha x. Okay, and if we take the first derivative of cosine alpha x, what do we get? We get minus alpha sine alpha x. Okay, we take the second derivative, then we end up with minus alpha squared cosine alpha x. In other words, we return the same function that we started with, along with some constant that goes before it. So if we look at this Schrodinger equation, what we find is the right-hand side of this Schrodinger equation is some constant. In this case, it's E multiplied by that same function. So in a nutshell, that's our Schrodinger equation. We're going to solve that differential equation, and we're going to find the various solutions. So job done, we've solved our Schrodinger equation, and now the next piece that we need to do is we're going to apply boundary conditions to refine the solution. So in principle, our two solutions were e to the alpha x. That's one possible solution. Another possible solution would be cosine alpha x. And it turns out that there's an infinite number of solutions in here, knowing that alpha can take an infinite number of values. So we'll see later how we can apply boundary conditions to refine this solution as we go on to look at the particle in the one-dimensional box. We'll think about something like butadiene, and we'll recognize that really in butadiene, there's only so much space that the electron can reside in, right? The electron is on the molecule, so we expect that electron to be within certain boundaries because it's sitting on this molecule. And by doing that, what happens is we start to refine our solution so that we end up with a single solution for our particular well-defined problem. So what was my point here all along? The point is to tell you about these rules of quantum mechanics. So describe your systems using classical physics. Substitute observables with corresponding quantum mechanical operators. From that operator, put it into the Schrodinger equation, solve the Schrodinger equation, and then we're later going to see how we have to apply boundary conditions to refine the solution to find an exact solution. So thank you for listening. This ends up being lecture 4, and we'll see you next time as we develop further these rules, and I'll explain where they come from. Thanks for listening.